Organic radical chemistry plays a major role in multiple ways, and I'd like to give you a list of those things and just give you a sense of just how significant radical chemistry is. Environmental chemistry, ozone depletion. That ozone layer, of course, is what protects us from UV light. The greenhouse gas effect relates to the chemistry of molecules trapping heat, resulting in global warming. Biological chemistry, primarily damage, leading to disease and food spoilage. Synthesis of key polymers, for example, polyethylene. These long chain compounds that can have really valuable properties and are used widely. Radical chemistry is one of the ways, less used today, but one of the ways that these polymers can be made. Introduction of a functional group on an alkane, and alkanes are so relatively unreactive that this is important. So look at that. There's no debating that organic radical chemistry is really, really important. And yet we don't devote a lot of time discussing organic or radical chemistry in this course. Most of our focus is on charge-driven chemistry, and there are reasons for that, just how important they are and how widely used they are. And we need to talk enough about radical chemistry that you have some sense of what organic radicals are and the chemistry that results from their properties. So let's first talk about what organic radicals are, what they look like, what their properties are, their chemical properties. We're talking about compounds that have a carbon atom with an unpaired electron. This is neutral. Carbon has enough electrons to balance the protons in the nucleus, but it doesn't have a filled outer shell. So right away you're going to think to yourself, this guy is going to be reactive. It needs to pick up one more electron. Absolutely true. Second thing you might wonder about is, what orbitals does that use? We talked about sp3 hybridization being the hybridization of choice to get 4 pairs of electrons away from each other. We talked about sp2 hybridization as being the hybridization that carbon uses to get 3 pairs of electrons away from each other. And here we've got a carbon atom that has, well, it's got 3 pairs and 1 other electron to get away from each other. So one might be tempted to think that this is going to be using sp3 hybridized chemistry like a alkane. But in fact, careful studies have shown that carbon radicals behave as if they were planar. I was careful not to call it planar, but we're going to act like they're planar because if they're not, they're collaborating between 2 different forms. And I've written these signal bonds in a plane perpendicular to the screen. And I can write this p orbital for sp2 hybridization in the plane of the screen. And then we could write that electron here, or we could write that electron in this lobe if we wanted to. But we're not going to spend a lot of time looking at the orbital that that electron is in because it's just not useful to us. But what is extremely important to recall based on this sp2 hybridization is that this is planar. So if this radical is made from some precursor where this carbon is a stereogenic center, that stereochemistry goes away, just like we talked about for the stereochemistry of making carbocations and the fact that SN1 chemistry leads to racemization. Well, the stereochemistry of radical chemistry is such that forming a radical at a stereogenic center leads to racemization. And further chemistry can happen either with this orbital lobe or this orbital lobe. Second thing I need to tell you about, carbon radicals are electron deficient. This might seem a little bit as a surprise because it's not charged, and we could easily understand how carbocation are electron deficient, but this uncharged radical is electron deficient too. And it is electron deficient because carbon wants a filled outer shell. It needs an octet and it only has 7 electrons in its outer shell. So these guys are electron deficient. One of the ramifications of that, then, is that tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals, which are more stable than methyl. So as we attach alkyl groups to this carbon, there is a mechanism for electron donation that lets alkyl groups donate a little bit of electron density to that electron deficient carbon. And so the argument for this order of stability that's observed, tertiary is much easier to form than secondary, much easier to form than primary, which relates to their stabilities. The explanation for that is the same as we talked about for carbocation. That if we were to look carefully at what it means to have an alkyl group here, we would notice that this carbon atom will have bonds associated with it, the sigma bond. And a sigma bond, let's say a CH bond, can share through space electron density. This is called a hyperconjugation. I'm revisiting it now because we haven't talked about it for a long time and it's important. It's the common explanation for why alkyl substitution on radicals leads to greater stability. Okay, so now we've talked about it. These carbon-centered radicals are planar. They're more stable when they're more highly substituted. How can they be formed? One of the ways that carbon radicals can be formed is through simple homolytic cleavage of a bond, where one of the electrons of this sigma bond, and we use a fishhook arrow to denote that, not the regular arrow with the two sides on the head. One of the electrons goes with carbon and the other one. Now this won't happen simply by itself. A carbon-hydrogen bond is a strong bond. But it can happen when something else donates an electron to form a sigma bond. And what would that something else be? Something else would be a radical. So once radicals are formed in the presence of organic compounds, that radical can do one electron abstraction of a hydrogen to form a sigma bond by one electron breakage of this bond. And that one electron breakage of a sigma bond is called homolytic cleavage. Talked about that a long time ago. And so in a case like this, the chemistry that results is the formation of a carbon radical and hydrogen bonded to what was a radical, whatever was here. And now you've got a carbon radical, and this radical can behave like a radical with radical chemistry. And typically that will be a one electron bond breakage of something else, which forms another radical. And radical reactions typically are chain reaction caused by homolytic cleavage to create one product and a second product that's a radical. And that product then, that radical, causes another step to happen, forming another radical, and so on and so forth. So that type of radical chemistry is very important. And by the way, one of the key radical components that we should mention is, are you ready for this? Molecular oxygen, the stuff we breathe. It can be represented as a diradical, two unpaired electrons. And this is the chemistry of biological processes that does damage, whether it causes disease or whether it causes food spoiling. The chemistry of oxygen radicals reacting with organic compounds in uncontrolled ways is the chemistry of disease. And so you hear a lot about eating antioxidants and vitamin C and so on and so forth. And those antioxidants are oxidizing compounds. The oxidations they're talking about are radical reactions of molecular oxygen with organic compounds that are biologically important, including DNA and RNA, which of course can lead to genetic damage if those compounds undergo radical oxidation. There are compounds that you can provide enough energy for in a specific way to simply cause the formation of radicals. Bromine is one of them. We make two bromine atoms, and it's homolytic cleavage. This can also be chlorine, same kind of thing. It also can be a dialkyl peroxide and a homolytic cleavage of that very, very weak oxygen-oxygen bond. An oxygen-oxygen sigma bond is much weaker than most of the bonds we look at. It makes alkoxy radicals. And then those alkoxy radicals, just like halogen radicals, can behave in this one electron chemistry up here, this homolytic cleavage of carbon-hydrogen bonds. So, because radical chemistry is typically the chemistry of chain reactions, the formation of radicals like this is a process that's often called initiation, because you're initiating chemistry that is caused by radicals in a process like this. A radical reacts with a normal molecule, hydrocarbon for instance, and that chemistry leads to the formation of a stable product plus another radical. And then this radical can react again in another step to form another radical and a stable product. And so this step is often called propagation. So we get propagation as a type of radical reaction. We have initiation, of course that happens first, to get radicals going, form radicals to get reactions going. And then there's a third type of reaction that is mechanistically the opposite of this one, where if two radicals find each other, of course you would predict that those guys could react because each has one electron to form a sigma bond. And so all of a sudden then we've lost our radicals. We don't have a chain reaction anymore. This ends the chain. And so it's easy to understand why this process is called termination. Okay, now you know the key things about organic radicals for our discussions about radical chemistry. They're planar, they're electron deficient, they're stabilized by alkyl groups, they can be formed by homolytic cleavage of bonds, they typically undergo reactions that are chain reactions in steps called propagation steps, where one radical reacts to form a stable neutral molecule, but in the process forms another radical. And those processes end when two radicals happen to meet each other and both donates electron to form a sigma bond to form a stable neutral molecule and no radical. You'll see that this is the theme for the chemistry of radicals that we talk about next.